All right. Good morning, everybody. Good afternoon. My name is Matthew Newstaden. I am a market development manager for cannabis environmental food and beverage markets here at SciEx, and I will be moderating today's webinar. This is session 3 of our 5-part PFAS testing series. We do have 2 more sessions coming up on June 2nd and June 23rd, so keep an eye out for those if you haven't registered already. Today's session, we're going to be talking about the power of accurate mass analysis and how you can implement that into your PFAS testing programs. So today's speaker is Dr. Karl Oetjen. And Karl has been with SciEx for quite a while now. He is, at this point, the Senior Technical Marketing Scientist for Food, Environmental, Forensics, Clinical, and Cannabis Applications. That's a lot of stuff that Karl covers. Before joining SciEx, he completed his PhD studies at the Colorado School of Mines with Dr. Chris Higgins, where he was focused on the non-target characterization of complex surfactant mixtures, which included aqueous film-forming foams, which are a source of environmental contamination with PFAS. So Karl's got a really good pedigree for this talk that we're going to be going through today. But with that, I think I'm ready to hand it over to our speaker today, Dr. Karl Oetjen. Karl?
Thanks, Matt. Yeah, so I'm excited to be talking about PFAS and high-resolution mass spectrometry. It's 2 of my favorite things, especially when they're combined together. So when we think about PFAS, in the past, right? In 2001, when we first sort of were diving into this topic and we're first sort of getting interested, we were thinking about specific compounds. We were looking for things like PFOA. We were looking for things like PFAS, very specific compounds that we wanted to analyze for. Whereas now we're sort of taking this a little bit more holistic approach, especially when we talk about high resolution mass spectrometry, where we're interested in characterizing some of these legacy or these novel compounds along with some of these legacy compounds. We know that there are things like impurities when PFAS compounds are created. What about those? What role do they play in the environment, in our communities? These are all questions that we're pretty interested in answering. And when we think about high resolution mass spectrometry and some of the workflows that we can do, they all revolve around what questions you want to answer. So that will be kind of the theme of what I'm talking about today is what questions do you want answered? Last time we spoke a lot about targeted analysis. So when we think of target analysis, we're really asking that question, is PFAS in my sample? Is PFOA in my sample? If so, how much? So we're really focused on the quantification usually. So if that's something that you're interested in, if that's the question that you're asking, then I encourage you to check out the last session. If you're thinking about other questions like, which one of these compounds out of this predefined list are present in my sample? I've got this list of maybe 12,000 fluorinated compounds that I know exist. Do I see any of these in my sample? So that would be a little bit more challenging of a question. All the way up to non-target analysis, which is as sort of broad as you can get, and you're just really asking the question, what is in my sample? That can be a really challenging question. It can take a lot of work. So you may be asking just, everything that's in my sample, or are you asking about just the fluorinated things in my sample? And the reason I distinguish that is because when we think about all the things that could potentially be in your sample, especially when we're talking about sort of these complex matrices, maybe we're talking about serum or 𝗔𝗱𝗃𝗃, or maybe we're talking about soils and foods. When we think about small molecules and just the wide variety that can be present in our sample, we're talking about hundreds of millions of different compounds. And when we think about their mass distribution, well, they're all kind of in the range where we might be looking. So when we kind of define our questions and think about our questions, we need to be thinking about, hey, what is it I'm looking for and what's the purpose of this data? That's going to dictate which workflow you do. But before we get started, there's going to be a couple things that I just want to define since we're going to be using them a lot. And the first would be mass accuracy. So mass accuracy, super important, but it's pretty simple. It's just the difference between your measured mass and the exact mass. So the mass that you measured on your instrument versus the mass that you calculated from the compound's formula. But one of the things I kind of want to bring to your attention is when we talk about mass accuracy, we're talking about it in parts per million. So if we have this compound here, which has a mass of 652.4116, the difference between 2 parts per million, which is usually what we're shooting for, is 0.0013 Daltons. So think about how small of a value that is. We're being really precise. And typically with high resolution mass spectrometry and for screening and non-target workflows, we really want to be below that 5 ppm error. And most of the time with modern QTOF systems, we're talking about sub 2 ppm. Another variable that we'll hear a lot about would be resolution. So resolution, again, incredibly important, but when we think about what it actually is, it's pretty simple. We're just taking the accurate mass or that measured mass and dividing it by the width of our peak. So when we think about what that means, as our peaks get more defined or get narrower, our resolution is increasing. So if we start with something like a 5,000 resolution, our peak is much more broad than if we go all the way to 100,000 resolution. And when we compare that to something like a nominal mass instruments, it's a big difference. So as we kind of continue, where this comes into play is as we go from 5,000 to, let's say, 50,000, the number of formulas that compound could potentially be, or that feature could be, exponentially decreases. So maybe with a resolution of 5,000, you're talking about, hey, that feature could potentially fit these 50 chemical formulas, versus 10,000, where we're talking about maybe that feature could fit 10 of these chemical formulas, and then all the way to maybe something like 50,000, where you're talking about it's really between these 2 chemical formulas or this 1 chemical formula. So as your resolution increases, you kind of get a bang for your buck there that we're going to kind of exploit when we do some of this suspect screening and non-target work. And finally, one of the most important things to me is how do we communicate this confidence? It's pretty easy when we're doing target analysis because we have standards, right? So we're very confident that this is the analyte of interest, this is PFAS. But when we're talking about this list of 12,000 things, many of these don't have standards. Standards don't exist. There's simply no way for us to be able to purchase it. So how do we communicate confidence to our customers? How do we communicate confidence to regulators, to ourselves, to our supervisors, et cetera? And this is something that the metabolomics world really kind of took the initiative back in 2004, where they started trying to come up with a scale of how do we communicate confidence to others, to our researchers, to our peers. And in the environmental world, we really rely on the Szymanski index, or the Szymanski confidence intervals. So what these are a way that we can kind of communicate to each other of how confident we are in a result. So the bottom, if we think of it as a pyramid, the bottom of our pyramid would be a level 5. This is when we just have a mass. So we have a feature with a mass. That's all the information we know. It's still important, but not a whole ton we can do with it at that moment. We're not confident in what it actually is. All the way up to a level 1, so sort of the top of that pyramid, which would be we have a reference standard, we've matched it, we're super confident in what we're looking at. And then a level 2, which would be more of a library match, versus a level 3 where we have a tentative structure, but maybe there's no spectral data in a library to match to. We don't have any diagnostic ions. So we're kind of stuck in that sort of gray space. So first, let's kind of just quickly review that targeted workflow. So that question that we were trying to answer of, is PFAS in my sample? Is PFOA in my sample? And when we think about what a triple quadrupole is doing, so this would be a nominal mass instrument, we are taking an ion, so in this case, our 215. We're using that first quadrupole to filter out all the other ions. We're allowing that compound to enter the collision cell, or Q2, where fragmentation is taking place. We're creating our fragments, and then we're going to use the third quadrupole to filter out for a specific fragment. So in this case, that 185. So pretty straightforward. We've talked about it a bunch at this point, but very specific. So how does a QTOF or high-res instrument differ from this workflow? And the answer is not a whole lot, at least not in the beginning. So in this case, we are again telling our instrument to look for that 215. So our first quadrupole is going ahead and is just filtering out everything that's not that 215 ion. We then have fragmentation taking place. So up until this point, nothing's changing. We have fragmentation in our second quadrupole. But here is where things change when we enter the TOF analyzer. So a TOF analyzer, and this is a super oversimplification, but it's what I like to use, is a TOF is a really, really good stopwatch and a really, really good measuring tape. Over the years, we've gotten great at measuring distance and we've gotten great at measuring time. So what we're doing is allowing those ions to enter and travel through a known distance, and we can then correlate the time it takes them to travel that known distance to their mass. And we can be very precise when we do that. So that's the main difference between just a triple quad MRM workflow and an MRMHR workflow. We're still doing the same kind of thing. We're still optimizing for collision energy, but we are kind of getting a different result because we have all of that fragmentation information that we can use, and we're going to use it a lot in the next coming slides. So I get asked this quite a bit. Why bother with the fragmentation information? If you have, really high resolution, you can be really precise with the mass. Where does the fragmentation information come into play? And it can be really valuable. So here's an example of some TOF data where we have a standard. And if we look at my matrix blank, well, there's two interferences that I haven't been able to get rid of with just my TOF data. So this would be no fragmentation, just relying on my accurate mass and my resolution. So we've got some sort of isomer. Likely we have something that has the same chemical formula as what I'm interested in, or it could. But with this information here, I really can't distinguish between it except for the retention time. So that's telling me it's probably got a slightly different structure, but it could have the same chemical formula. So there's not a lot I could do when it comes to TOF or just the MS1 data there. But when we look at the MS data, well, it did have a different structure. It didn't create a specific fragment that I know my standard creates. So now in my matrix blank, there's nothing there. But when I look at my spike sample, I have my two beautiful peaks. So that's one example of how we can use MS data. That's super valuable. And we're going to show a couple more too. So for that targeted workflow, right, we're matching to a reference standard. When we think about where we're starting on that sort of confidence pyramid, we're really starting at that level 1. So we have a reference standard. We can be very sure that, yes, this is indeed the compound I'm interested in. I've got all my key variables. And those sort of pieces of confidence, or those pieces of information that we're going to use to say, yes, this is indeed PFBS, aren't going to change too much between non-target analysis, suspect screening, and targeted analysis. Some we won't have, but the others we're going to rely on heavily. So typically we would rely on the mass accuracy. Here, my standard and my compound or my unknown sample match very well. So starting to get more confident this is PFBS. I've got my retention time. So yep, they're eluting at the same time. That's great. I've got that fragmentation data because I collected all the data from those fragments. I can do a library match. So I kind of have the fingerprint of this compound. And then if I wanted to, I could even do an ion ratio just like we would with the triple quad. So I'm very confident. I'm at my level 1. This is definitely PFBS in my unknown sample. But what if we wanted to ask another question, somewhat of a more broad question? So I've got this list of 1,000, 2,000 different fluorinated compounds. Are any of those compounds present in my sample? I don't have standards for them. I probably can't purchase standards for them. They don't exist. But I want to screen my sample and figure out if they're there. So when we do this, we're going to do a slightly different experiment. And this is kind of important. So the first experiment we're going to do is just a TOF MS experiment. So in the past, we were telling our instrument, hey, I want you to look for this 215 ion. Whereas in a TOF MS experiment, we're not doing that. We're just allowing any ions to pass through Q1. We're not filtering anything out. And we're also not doing any fragmentation in Q2. So no fragmentation is occurring. We're just looking at those parent ions, and we're going to need those in the next section. So we've got our parent ions. Just like before, we're measuring its mass based on how long it takes them to travel a known distance. But what's next? So we've got a parent mass. I just made a big point about how important that MSMS data is. How do we collect that? And that's where it's going to vary just a little bit. So there are two approaches for collecting MSMS data in this fashion. The first would be information-dependent acquisition, where we're giving some sort of information to our system. And the next would be a data-independent acquisition approach. For our case, we're going to talk about SWATH, since that's what we do here at SciEx. But the theory of it is all going to be the same, and the way you use that data is going to be the same. So what is information-dependent acquisition? And essentially what we're doing is we're giving our instrument some sort of criteria that must be met for something to happen. So we've done our survey scan and we're saying, hey, this criteria must be met, whether it be a neutral loss, but 99% of the time is going to be an intensity value. If that intensity value is met, we're going to be doing an MSM experiment on those ions. So I've got a little example of that here. So here's my TOF-MS. So at a given point in time, these are all the ions that ionized and made their way to the detector without any fragmentation taking place. So these are all the parent ions. I'm going to set my intensity threshold. So here I set it at 3.7 to the 5-ish. Typically, this would be somewhere around 100 CPS to maybe 1,000 CPS. But in this example, it's a little easier to make it higher. And any of the ions that are above this threshold, I want to collect MSMS data on. So the instrument's going to go ahead and collect MSMS data on those 4 ions. So I'm happy I have my data, I can move on. I've got my TOF data and I've got my fragmentation data. SWATH's a little bit different though. In SWATH, or data independent acquisition, we're not giving our instrument any sort of information about what to collect MSMS data on and what not to. Here we want to collect MSMS data on essentially everything. And we're going to do that by using a sliding window. And we're going to really rely on that first quadrupole to create that window. So I've got my little animation here, and this represents a mass range from 100 to 500 MOZ. And I'm going to create 20 SWATH windows. So what I'm doing is in my first scan, so I've already done that survey scan, so this is my first MSMS scan. Anything with a mass between 100 and 120 M/Z is going to be allowed through my Q1, it's going to enter my Q2, and fragmentation is going to take place. In my next step, anything from 120 to 140 is going to be allowed through my Q1. Into Q2, fragmentation is going to take place, and so on and so forth. So I'm going to slide that window through my mass range. And we can set it up like this, where we have defined single units where with every window is 20, or we can be a little bit flexible. So here's an example of a SWATH method I use for PFAS analysis. And one of the things you'll notice is that the windows aren't the same values. So for example, in the 850 to 1,000 Daltons, I'm not really expecting a whole bunch of compounds. So I might make a really wide window there versus here where I have PFAS and PFNA. They elute at a pretty similar time in this really quick drinking water method. So I don't want to have to extend my gradient. I want my method to be as fast as possible, so I can't get any more chromatographic resolution, or I don't want to, I'm unwilling to. But instead, what I can do is make my windows at different units. So ensure that, for PFAS, for example, and PFNA, those two compounds don't elute within my window, or they aren't in the same mass range as my window. And this helps so I don't have spectra sort of overlaid on top of each other. There are approaches that you can do to make that not happen. So all software, I think at this point, has deconvolution software or deconvolution algorithms that will sort of remove extra fragments that don't belong to the compound of interest. But here I have the ability to just ignore that. I can just upfront make sure that problem doesn't happen. And with suspect screening and non-target analysis, flexibility is really important. So we want to kind of exploit anytime we have flexibility to meet our goals and answer the question that we're trying to answer. So just a little recap of what's happening. So we're doing the same experiment. We're doing an MSMS experiment. The difference is happening in how we select what ions we want to fragment. So here, instead of specifically saying, hey, only look at 215, we're just saying if an ion is between 200 and 250, for example, which in this case 215 is, then allow that to pass through Q2, then have fragmentation take place, then have those fragments make their way to the TOF analyzer. So same idea, just the way we're selecting which parents to fragment is a little bit different. And the reason we have two approaches, or the reason you might choose one approach over the other, is going to depend a little bit on what you're up to. So if your goal is to create a really high quality library, when I do that, I typically use information-dependent acquisition, or IDA, data-dependent acquisition. And that's simply because I'm collecting the highest quality spectra, and also most of the time I'm injecting a standard or maybe a reference material. So if I need to, I can inject more, I can lower my threshold, my sample's not that complex. So I can take advantage of those descriptors of my sample and sort of use this information-dependent acquisition to get the purest quality spectrum. Versus if I'm doing something like a library screening. So let's say I have a really complex sample. I want to collect MSMS data on everything. I would hate for me to set a threshold that's too high, and there's an ion that is just below it or quite a bit below it, but it's the most important feature. I really needed MSMS data on that to be able to identify it. And there's a chance with information-dependent acquisition, I just wouldn't have it. The other thing that I think is super important is the ability to archive your data. So in the past, right, we stick our samples in a -80, where they sit for anywhere between, at least in my experience, 10 to 30 years before they eventually get thrown out when the freezer gets thrown out. But here we have the ability to actually just archive those digitally. So we can go through and investigate or ask new questions, interrogate our samples in a different manner. So an example of this was I was doing some work in the past on 𝗱𝗱𝗱𝗶𝘶, and we were trying to identify new PFAS compounds in that 𝗱𝗱𝗱𝗃. So we ran all our samples, we ran it using SWATH analysis or data independent acquisition, and we found about something like 200 new fluorinated compounds, published a paper and all was good. And then a few years later, there was a master's student who had a different question, and she was really interested in kind of investigating the hydrocarbon surfactants present in those samples. So instead of having to go find those samples, dig them out, re-inject them, we just used the same exact data files, and she processed them and answered her question, which was unrelated to the question we were originally trying to answer. So being able to archive those samples digitally was really valuable. But regardless of which approach you do, your workflows you can do either with. So you can do a suspect screen with information-dependent data, or you can do it with data-independent data. Regardless, it's just going to depend a little bit what you're going to use the data for. But let's talk about some suspect screening. So here, again, we have that list. It's our predefined list, and we're just trying to say, hey, are any of the compounds on this list present in my sample? So if we go back to that confidence pyramid, here, instead of starting at a level 1, we're really kind of going to be starting at this level 3. So we've got a formula. We've got a mass. Typically, we have a formula. So we can screen versus that. That's really the criteria for a suspect list is we need a mass. Otherwise, we can't interrogate our data. But the majority of the time, in most suspect lists, since these are known things, we're also going to have some structure information. And if we're super lucky, we'll have something like an issue key. So we have a lot of information on that compound. And with that, we can go ahead and search that survey data and say, or that TOF-MS data, say, hey, do we see that formula? Is that formula present? Some of the places we can sort of curate or build these suspect lists from, the first one would be a library. So we have a library. In this case, it's just as an example, we have this IX fluorochem library. There's 252 PFAS compounds in there. And in my lab, I certainly don't have 252 standards of PFAS, right? But I can go through and screen my sample for all of those compounds and see, does it match my library? And if it does, I can be really confident, hey, this is a level 2 match. I'm moving up my pyramid. So here we've got some 6.2F2S, and we screened an unknown sample, and we're going to use the same criteria we talked about earlier to decide if, yes, this is truly 6.2F2S. So we've got our mass accuracy. Again, we want that to be under 2 ppm ideally, but under 5 is acceptable. We've got our isotopic information from our formula. That all looks good. And then we've got the fragmentation data. So we've got sort of the compound's fingerprint. So I can be really confident, yes, I get to move from a level 3 to a level 2. This is indeed the compound I'm looking for. So this is a really nice way to create a suspect list, and probably the easiest way to get started in suspect screening using a library. Or we can take a different approach. So here we can do something called database searching. We have these wonderful databases. Here's an example of one, the US EPA's ComTox. They have 39 PFAS lists. Some of them have 12,000 different fluorinated compounds on them. They're pretty extensive. So I can take one of these lists and interrogate my data and say, hey, do I see any of these compounds present in my sample? And that's great. But one of the things you're probably realizing is that I don't have that library data to lean on. So I don't have that spectral information, right? I've got my formula, which is what I need for a suspect list, or at least a mass. So I can do my mass error. Presumably I have a formula, so I can match my isotopic information. So how do I ever move past that? How do I climb up the pyramid further? So again, for library searching, we rely on that spectral data, but here we're going to have to do some spectral interpretation. And we're going to rely on some tools to really help us along. So there are a few different tools that you can sort of access. These are all the ones listed here: CFMID, MetFrag, CSI Finger ID are all open source third-party tools that I encourage you to check out. They're all free. But we're going to rely on these essentially to make our identifications. And the one I personally use the most is probably that CSI Finger ID. And there's a couple of reasons why, and I'll kind of go over them, but it's a super valuable tool, and I encourage you to check it out. And the main reason I'm using this spectral interpretation tool is because of the graphical interface it lives in. So CSI Finger ID is an algorithm. And essentially what that algorithm is doing is you've fed it, or really they've fed it, a database. So they had a database with formulas, structures, et cetera, and fragmentation data. And using some machine learning, they essentially were able to predict the way these structures would fragment. And now what they're doing is taking that data, or that sort of prediction tool, and applying it to unknowns. So in our case, when we're searching the ComTox, for example, we have a structure, we have the mass, we have the formula, but now we want to know, do the fragments we're observing make sense? And that's where we can lean on tools like SIRIUS to do that. So here we would input all that data, so that MS1 and MS2. We could even put it in our structure and use that tool to say, hey, do these fragments make sense? Are they things we would predict when doing CID? Can we be confident enough to move into that level 2 zone where we have a diagnostic ion even? So that's one of the ways, if you don't have spectral information, you can sort of climb up that pyramid a little bit further. But what about our last question? So sort of the most complex and a really interesting and time-consuming question that has a lot of value of what's present in my sample. So we've got this sample, let's say it's an 𝗔𝗱𝗃𝗃. We've run it on our QTOF, and now we have 5,000 features. And we want to know, hey, what's in this? So for this, we would be doing a non-target workflow. So we're going to do some peak detection and move through and hopefully get all the way up to a level 1. But we'll be at varying states in the pyramid just based on what's available to us. So when we think about confidence, where are we starting? Well, we are starting at the bottom of our pyramid. So we are starting at level 5. We essentially just have a mass. We don't have any other information. So what's next? What do we do? Well, first we have to figure out, are we going to do a non-target workflow? So we've got that feature mass. The way we acquired it has to be acquired in a very specific way for it to be considered non-target workflow. And it really relies on 2 variables. So the first would be the acquisition type. So we need that survey experiment. We don't technically need the MSMS data for some workflows, but in all honesty, we really need it. We're gonna lean on it, especially when we're doing identification. And we need to do our peak detection in a very specific way. So previously we had a list that we were telling our software, whatever that software might be, hey, look for these compounds, see if they're present. Or in the MRMHR workflow, traditional triple quad, we're telling the instrument to, hey, just look for these things. We don't want to do that when we're doing a non-target workflow. We want the software to pick anything that it decides is a feature. And the algorithms are pretty advanced. They can vary a little bit, but essentially what we're doing is we're trying to limit our bias. With non-target workflows, limiting your bias is one of the more important things you can do, but it becomes challenging, right? When we think about just the fact that we chose an LC high-res system instead of a GC high-res system. We're using ESI, for example. So we're already biased towards some of the more polar compounds compared to if we did GCMS. We're doing EI for an ionization approach or APCI. So we're already leaning that way. One would argue for fluorochemical analysis, it's probably not a big deal. But even everything from just the column that we chose maybe a C18 column, and it's not great for some of those new short-chained PFAS compounds that we're interested in. We're always introducing bias, but we want to really limit it as much as possible. So once we have our features picked out, the first thing we're going to want to do is get rid of some of the ones we're not interested in. And that's called prioritization. There's going to be, if you have a complex sample, there might be thousands of different features present. So how do we get at what's important to us and what's important to the question we're asking? So in this case, we're talking specifically about PFAS. So I'm just going to kind of go over some of my favorite ways to get at that. You're specifically interested in fluorochemicals. So the first approach would be to do a homologous series screening approach. So this is a tool that you can access via MVMass or R. If you have R, it's called non-target. MVMass is a software that you can just go ahead and type it into your Google browser and bring it to it. And you can do this type of workflow. But what this type of workflow really is relying on are these mass differences. So we know most fluorinated things, they're just polymers, right? So they're changing in a lot of cases by the CF2 group. So we can have this script essentially go through and identify any feature. So we've got just a mass and go through and look, do we see any features that vary by the CF2 group? Or in this case, we're being very unbiased and we're saying we want to see features that differ by the same amount. So this tool is going to look at all the features in my sample and say, hey, I've noticed these 4 features all differ by a CF2 or a mass of 50. And not only that, they all differ by the same retention time difference. So if we're using sort of a traditional gradient where we're just going from 0 to 100, we'd expect that retention time difference to be the same too. So we can use that to pull out what's important to us. In this case, we have 4 compounds or so. We know the structure of one of them. Well, now we know the structure of the other 4, simply because we know it's a homologous series and it's differing by that CF2 group. So that's an easy way to sort of climb up our pyramid from having no idea what this feature is to very quickly having some diagnostic evidence getting to that level 2B. So homologous series screening is a really valuable tool, but you can use this to look for other hydrocarbon surfactants as well, or anything that's sort of a polymer. If you really wanted to dial in though, let's say you were getting too much information. There were too many series for you to look at, and you really are asking the question of, hey, I'm only interested in fluorinated compounds. That's where something like a Kendrick mass defect screening approach can be really valuable. So Kendrick mass defect screening, really all we're doing is we're normalizing to a repeating unit. That can be any repeating unit. In the case of fluorochems, we're usually choosing CF2. So what we've done is we're normalizing all our data to that repeating unit of CF2. And what you'll notice when you do this is that any features that differ by this mass should form a straight line. So we've got some examples here. We've got some perfluorinated sulfonic acids, all falling along the same line, all just differing by that mass of 50. So this is a really nice way for me to go quickly and say, hey, I'm only interested in things that are fluorinated. And it also gives me a little bit of information, right? If I know one of the compound's identity in this series, well, I can go ahead and identify the other ones because we're just talking about that mass shift of CF2. So again, you get sort of this really nice reward for just knowing one structure, and all of a sudden you know 5 or 6, and you can move up the pyramid really quickly. Another pretty common and kind of newer, I would almost say, approach to sort of prioritizing data would be using diagnostic ion filtering. So diagnostic ion filtering, what is that? We're looking for a specific fragment. In the past, this has been really valuable in looking at things like fentanyl analogs. So if you think of fentanyl, you can think of like different versions of fentanyl that have been synthesized to not be fentanyl. So maybe you added a methyl group, for example, or an alcohol. But fentanyl's backbone is always going to be the same. So some of those fragments are always going to occur, even though the mass is slightly different because you've added a methyl group, for example. And the retention time is different. So you would never know to look for that compound. But it was pretty successfully used to screen for new analogs of fentanyl because we can just look for that fragment. So we were looking for that diagnostic fragment that tells us that that backbone exists. And we can do the same thing in fluorinated analysis. So we're looking for specific fragments that are unique to PFAS compounds. Or maybe even you want to get more specific and you want to prioritize things that are have a sulfate group or amine compounds. We can look at very specific fragments that occur when we have those kind of structural components. So here, it was a paper published in 2017. They did exactly that. They were looking for things like the C3F7 group. And sure, they didn't know to look for all 8 of these features, but they essentially got 8 features for free by just looking for that fragment. So instead of looking for a parent mass, they're using that MS data that's so important to screen that first, and then sort of almost kind of work backwards to a parent mass. And when you do this, you get a lot of information, but you have a lot of information already since you have information on that diagnostic ion. But regardless of what sort of approach you take or how you go about screening your data, prioritizing your data, it all comes back to those questions of what is the goal of this data set? How am I going to search through it? So if my goal is to only look at fluorinated compounds, maybe doing something like a suspect screening approach might work really well, especially if we're looking at, maybe a soil where we're not expecting new fluorinated compounds. We have lists of 12,000 things. Those are the ones that are the most prevalent. So I want to look for those. That is a totally great workflow versus maybe you're looking at human systems where you're trying to identify metabolites or something unknown. Well, then you might want to do one of those non-target workflows. But again, regardless of the systems, when we're talking about high resolution mass spectrometry, specifically non-target analysis, these systems are really complex. So eventually we're going to have to decide what's good enough. How much do I really need to characterize my system? That way we're not spending, decades looking at a single sample. And with that, I would like to just kind of plug the next session, which is going to be PFAS in people. So Dr. Craig Butt will be leading that session. And it should be pretty interesting considering that we all have PFAS in our blood. So learning a little bit more about PFAS in people should be a kind of a fun topic for us to all chat about. And with that, I'm happy to take any questions.